Newton's second law of motion. The one, the only. You'll notice that for this one I don't have the original Latin because math is a language that supersedes language. And we can describe Newton's second law of motion with a very simple mathematical equation. Before we do so, though, let's refresh our memories, recalling from previous discussions the law of inertia, which is, of course, Newton's first law of motion. And you'll recall that the law of inertia says that an object at rest will remain at rest, and an object in motion remains in motion unless acted upon by a net force. Now, our previous scenarios have all involved a zero net force, or situations where our forces are balanced. Now we're going to start looking at situations where the forces are unbalanced. Newton's second law, the actual equation, tells us that the acceleration of an object is directly proportional to the sum or the net force acting on the object and inversely proportional to the object's mass. And that eloquent, amazing, delightful mathematical expression can be seen here. Now this seems fairly straightforward. It's only 3 variables. A little bit of algebra, we're good to go. What we will find challenging is this piece here, finding the sum of the forces. We're going to be working in both 1 and 2 dimensions, and we're going to have to keep in mind that our forces are in fact vectors, and with vectors direction matters. Now as we look at this, we see that we have mass and we have acceleration, and so our units for force based on this particular formula should be kilograms times meters per second squared. This unit, or this set of units, kilograms times meters per second squared, has been compacted into what's called a derived unit, which is the Newton, symbolized with a capital N, of course in honor of Sir Isaac Newton, the one, the only. So, sigma F, the vector sum of all external forces acting on an object. All that really means is we have to take into account every force acting on an object when finding the total force. What we do find, and if we notice that both acceleration and net force are both vector quantities, what we do find is that the direction of those vectors, the net force and the acceleration, are always the same. Okay? Always, 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 and forever the same. Now, because the acceleration is directly proportional to the net force, we can also see then that if the net force is 0, the acceleration is 0. If the acceleration is 0, what does that tell us about the velocity? If you said it tells us that the velocity is constant, gold star for you. Because if we recall the definition of acceleration, acceleration is the rate of change in velocity. If the rate of change in velocity is 0, that means that there's no change in velocity, which means that it's constant. This is what we were looking at earlier in the year in our constant velocity particle model. It was also our balanced forces particle model. All right? So now we have a situation where the forces are unbalanced and our acceleration is constant, or constantly non-zero. Okay? Now, in terms of writing these things out, this sigma F we will typically write as F net, or the net force acting on an object. And again, as always, our subscripts are there to help us distinguish between different forces. Please, please, please do not confuse F net with the normal force. Okay, so those are 2 very distinct forces. Now, just as a follow-up to our discussion on units that we just had, as we said, 1 Newton is 1 kilogram times, that should be here, I would think. 1 kilogram times meters per second squared. Now, for you, practically speaking, what this means is that when doing calculations, when solving for accelerations or masses or things like that, we have to recognize that the mass should always be in kilograms and our acceleration should always be in meters per second squared. So you might have to convert going into calculations. Just to put it in a little bit of perspective, because we're not necessarily used to using newtons as a measure of force, 1 Newton is about 0.225 pounds. And remember that pounds is simply the English unit for force. So when you talk about your weight, if you're 150 pounds, what that really means is that the earth is pulling down on you with a force of 150 pounds. And the other way to look at this, 1 pound of force is about 4.45 newtons on Earth. Okay. Saying on Earth is actually fairly important. We'll get to the why there in just a few minutes. But before we do, let's take a look at a quick practice problem. 2 boys are pulling a 5.2 kilogram wagon in opposite directions. Boy 1 is pulling to the right with a force of 38 newtons, and boy 2 is pulling to the left with a force of 17 newtons. What is the wagon's acceleration? Take a few minutes, see if you can do this on your own, and then we'll go over it. Okay, first step, draw our free body diagram. Okay, so we're going to figure out what's important. It's the wagon, that's what we're looking at. So let's draw the free body diagram for the wagon. Let's use blue. Let's see, how's that? That stands out much better. Let's use that. So, boy 1 pulling to the right with a force of 38 newtons. Remember that vectors should, at least qualitatively, represent the magnitude of the vector by their length. So we're going to draw the one to the left smaller, a little less than half smaller. So net force is equal to the sum of all the forces. In this case, it's easy. It's just one dimension, right? So I'm going to call, in my frame of reference, left positive, right negative. So that's going to be the force of boy 1 plus the force of boy 2, which is going to be 38 newtons plus a negative 17 newtons because it's in the opposite direction. So 38 newtons, simplify to minus 17. So 38 minus 17 is going to be 21 newtons. So the net force acting on the wagon is 21 newtons. Okay? We want the acceleration. We know that the acceleration is the net force divided by the mass, which is equal to 21 newtons divided by a mass of 5.2 kilograms, which, when we plug this into our calculator, gives us 4.04. Now, looking at this, we have 2 significant figures, so we're going to round. We're going to call that 4.0 meters per second squared. But again, because acceleration is a vector, we have to include direction. So 4.0 meters per second squared to the right. And so there's our acceleration. Okay. Now we'll do more practice problems in class, so certainly more like that, and then also some in 2 dimensions. As I mentioned earlier, we have those conversions of pounds to kilogram, or rather pounds to newtons, and how they compare. But it is important to understand that that is actually only applicable on Earth, because that gravitational force is coming from Earth. Now, as we mentioned previously, just as the Earth is pulling down on you, right? So there is the force of gravity down on the Earth. You are also pulling up. So we'll say Earth on you, E on Y. You are also pulling up on the Earth. So it's the force of gravity of you on the Earth. And you're exerting just as much force on the Earth as the Earth is exerting on you. The difference, and we mentioned it just recently, the acceleration is equal to the net force over the mass. When we're talking about you, we have some reasonable net force over some reasonable mass. When we're talking about the Earth, though, we have some reasonable net force over a fairly enormous mass, which is why when you jump, the acceleration that you notice is yours, not the Earth. You don't notice the Earth accelerating up towards you, except in that you are falling towards the Earth. So even though you're exerting an equal and opposite force on the Earth, per Newton's third law, the Earth doesn't accelerate in any noticeable fashion because of its significantly larger mass. Now, that acceleration that we experience is, and we might know this from other situations, 9.8 meters per second squared, roughly. That's the acceleration due to gravity, or little g. That 9.8 meters per second squared comes from the force of gravity acting on an object. The force of gravity is directly related to the mass. So what that means is if the mass of an object doubles, that the acceleration, or excuse me, that the force doubles. And so from our acceleration equals net force over mass, if the mass doubles, then the net force, the gravitational force acting on it doubles, which means that the acceleration stays the same, which is why, as Galileo discovered, all objects accelerate towards the Earth at the exact same rate, no matter their size. Now, where this falls apart is when you have things like air resistance. And we can get into that a little bit more and how air resistance affects different objects. The other thing that's interesting is that weight is a field force, and it's also actually one of our fundamental forces, one of our 4 fundamental forces that we talked about. And it's a non-contact force. So you don't have to be in contact with the surface of the Earth in order to experience gravity, which is why things fall, because you jump off a desk, you're no longer in touch with Earth, but you're still falling, and that's where you get into relativity and warping of space-time and a lot of other really interesting, hard to understand aspects of physics as well. With this, though, the one thing that I really want to make sure you guys internalize and understand is that weight and mass aren't the same thing. Okay, mass, first of all, mass is measured in kilograms, right? And it's a measure of the amount of matter that makes up an object. Weight is measured in newtons, and it's a measure of the force of gravity acting on that object. And so if we were to stand on the surface of the Earth and then somehow instantaneously, magically be transported to the surface of the moon, in both situations, your mass is the exact same. You have a mass of maybe 75 kilograms, right? Because there's 75 kilograms worth of matter, of material, of atoms that make up your body. But because gravity is a direct result of the mass of the 2 objects involved, when you go to the moon has significantly less mass than the Earth. Because it has significantly less mass, there's a much smaller force of gravity between you and the moon. And as a result of this, you feel lighter. You're still made up of the same amount of stuff, But the weight, if you were to step on a scale and take your weight on the moon, it would be much less. Okay? So regardless of where an object is in the universe, its mass is going to be the same. Depending on what objects are around you, your weight is going to be different. And so mathematically, because the moon has a mass that's about 1/6 of the Earth, your weight on the moon is going to be about 1/6 of what it is on Earth. So make sure as we go through calculations and investigations and things like that, we keep those two terms separate and distinct. Mass in kilograms, measure of the amount of matter. Weight, measured in newtons, a measure of the force of gravity acting on an object's mass. Make sure you've taken good notes. Write down any questions you might have. We'll talk about them in class. See you soon.